So in last session we discussed that how we can describe the plane curvilinear motion using rectangular coordinate system, XY system, right? We saw that we can consider a curvilinear motion when described in rectangular coordinate system. We can consider it as a sum of two simultaneous rectilinear motions in x and y directions respectively. Now we will proceed that discussion further and introduce another way of describing the plane curvilinear motion, and that will be using normal and tangential coordinates or NT coordinate system, right? So I will be introducing what NT coordinate system is and how we can describe the motion of a particle which is moving in a curved path using this new set of coordinate system, normal and tangential coordinates. So first thing is that this NT coordinate system is a natural way of describing curved motions, right? So it's a natural description of curvilinear motion, and that description is in the form of what we call as path variables. So we will be describing curvilinear motion in terms of or using what we call as path variables. And path variables means that we will be providing or describing the motion using measurements along the tangent and normal to the path of the particle, right? So path variable means measurements made along the tangent. So tangent will be represented by T, tangent direction, and normal, which we will be denoting with n, small n, to the path of the particle, path of that curvilinear motion. So we will be describing this motion using measurements along t axis and along n axis, where t and n are the tangent direction and normal direction respectively to the path of that particle. So if a particle is moving from point A to some point B in a curved path, and then from B to some other point C in a curved path, at any time instant we can have these two directions. One will be tangent to the path, we will be denoting it with t direction, and the perpendicular to that tangent, which will be normal direction, right? So t and n will be our new directions, and measurements along each of them can describe this curvilinear motion. Now the first thing you will be noticing here when you compare it with the case of rectilinear motion, that our xy coordinate system, there they were like fixed and the particle was moving relative to the origin, right? So we use the position vector to describe the location. Now here our n and t axes are moving with the particle, so they are also changing their directions all the time as the particle moves in that path. So at one time instant t will be having one direction, n will be having 90-degree angle with that t. Similarly, the next time instant the t will change its direction, so the axes are moving with particle now. This is one major difference in using these coordinate systems or path variables, right? So first of all, n and t, they move along the particle, move along the path, right? Now the positive direction of n will always be towards what we call as the center of curvature. So for example, if particle moves from A to B in a curved path, so you can see that it is concave upward, that path is concave upward, right? So positive direction of n will always be towards the center of curvature. So actually what I draw here, these two n directions, they will be positive, right? So this is positive direction for n axis. and that will always be towards the center of curvature. So towards some center of curvature, which will also be changing, by the way, all the time, right? So from B to C you have a concave downward curve, right? So the center of curvature will be a different point. So from B to C you will see that this direction is actually positive n direction, right? So this is positive from B to C because it is concave downward and center of curvature will be somewhere here, for example. For A to B it may be somewhere upward or above this curve, right? So towards center of curvature. Along that path there can be some points in which you don't have a curvature. For example, imagine a point here where you don't have curvature. What is that point called? Inflection point, right? Where actually a curve changes its concavity from maybe concave upward to concave downward, or from concave leftward to concave rightward. So for example, this is our point of inflection, right? The curve is changing its concavity here, so it's point of inflection, right? So we can still have tangent at that point, and that will be exactly like this will be the t direction, right? What about n? Because currently at this point there is no center of curvature, right? So there is no n component of acceleration when you have the point of inflection, right? So the n component of acceleration vector will be 0. So if I call a sub t as the component of acceleration vector along t direction and a sub n the component of acceleration vector along n direction, then at the point of inflection a sub n will be 0, right? So exactly a case like when in xy coordinate system you can have certain points along the path in which x is 0 while there is some value of y, or when y is 0 when there is some value of x, right? Same is the case here. So along the path at the point of inflection the n component a sub n will be 0. So this was a quick introduction of n-t coordinate system. They move along the path and they vary their direction all the time, right? And the positive direction of n will always be towards the center of curvature. Now after this introduction, let's now describe velocity in terms of n-t coordinate systems, right? This is what we did for xy coordinate system also. So if I give you a quick summary, maybe towards the left side, maybe here, if you remember xy coordinate system, after defining this system, the first thing we did was to see how we can describe velocity and then later on acceleration in this coordinate system, right? So if you remember, we started with a position vector r, which is equal to x times the I vector plus y times the j vector, and then we say that velocity vector can be written as, when we take its first derivative with respect to time, we came up with this expression x dot times I plus y dot times j, right? Similarly, we repeated that derivation one more time to get acceleration, and it came out to be x double dot times I plus y double dot times j, right? So this will be y double dot times j. So actually we saw already that how to describe velocity and acceleration in xy coordinate system. We can do same thing now in the n-t coordinate system also. So we want to now determine what is the t component of velocity, what is the n component of velocity, so that we can write the velocity vector as a sum of its t component and n component. Similarly, we would like to know what is the t component of acceleration of a particle moving in a curved path and n component of acceleration, so that we can write acceleration vector as a sum of its t component and n component. So in order to do that, first let's define few notations. So a particle was moving from point A, and then at next time instant it moved to A prime, and it is following a curved path, which is this curved path, right? So this is the path of the particle, and at two different time instants its location was actually A and A prime. The value of the velocity vector at point A will be denoted by v vector, and similarly the velocity vector at the A prime. So this is v vector, then this is v prime vector, and if you consider A prime as an arc which is part of a big circle, then you can also locate the center of curvature. So let's define capital C as the center of curvature, right? And we also know that if we have an arc having length, for example A prime, and that arc is part of a big circle which is making an angle theta at the center of that circle, the length of that arc is equal to the radius times this angle theta, right? So if I call this distance from some C to A as r, and then the length of this arc A prime will simply become r times theta, right? Or if I denote it with small l, then L will be simply r times theta. So if we denote the radius of curvature with rho here in this case, so rho is the radius of curvature, it is the radius of a big circle which is actually having an arc A prime, then we can write this distance ds, this distance A prime, as rho times d beta, where d beta is the differential angle between those two time instants, right? So when the particle was at A and when it moved to A prime. So the angle which it is making, the radius of curvature is making with the center, at the center of curvature, is denoted as d beta, right? I can write this distance ds as rho times d beta. Now we have two coordinates also. One is t axis, right, which is tangent to the path at any given time instant. So at point A, this will be the direction of t, which will also be the direction of velocity vector. At the time instant when A moved to A prime, the particle moved to a new location, you will have a different velocity, but now you will also have a different t axis. So it may be called as like t prime, right? Similarly, at both of the points, you will be also having n axis, right? So n axis here or n axis at A prime also, it will always remain 90 degree to the corresponding t axis. So we have now defined some new terms here: radius of curvature, center of curvature, the differential angle which the particle's motion actually made at the center of curvature, and the arc length or the distance which it actually moved from point A to A prime. I denote it as ds, and that will be equal to the radius of curvature times the differential angle, so rho times d beta, right? Now let's introduce two new unit vectors, each along one of the coordinates which we are having now, which is n and t coordinates. So along t coordinate or t direction, let me introduce a new unit vector and call it E sub t, and a small cap on it, indicating that it is having a length equal to 1 and it is a vector, right? So E sub t is a unit vector in the t direction, length equal to 1 but direction is t direction. Similarly, E sub n here is the unit vector in the n direction, normal, right? E sub t and E sub n, they are changing its direction all the time, right? But at one time instant we can call them as E sub t, E sub n. Maybe at A prime we can call a unit vector in that direction as E prime sub t, and similarly I can call the 90 degree to that as E prime sub n, right? So E sub n is the unit vector in n direction, right? And E sub t is the unit vector in t direction, right? Now, one fundamental difference between the I and j vectors, the unit vectors along x and y here, and En and Et vectors is that here I and j were having constant magnitude as well as constant direction. I will always be in x-axis direction, j will always be in y-axis direction. But here E sub n and E sub t are changing their directions all the time, right? So this is one major difference between the unit vectors introduced in xy coordinate system and the unit vectors introduced in the nt coordinate system. So this radius of curvature will have the dimensions of length, it is a distance, right? Similarly, ds is also a distance. D beta is an angle, so it should be in either radians or degrees, right? So it should have the units of radians or degrees, it is an angle, right? So please keep that dimensions of each quantity in mind also, right? We are actually assuming a case of differential increment from a to a prime, right? So we are assuming that the time distance from a to a prime is dt, right? So please note that this d beta is happening actually, this movement or this rotation is happening in a corresponding time of dt, right? So it is a differential angle in the differential time, right? So we will be dealing with a limiting case when time is approaching 0 between a and a prime, right? Now we are ready to define velocity in terms of n and t coordinates using this new notation which we just got familiar with. We know that velocity is equal to the change in displacement between the time which is being considered, right? So it is the rate of change of displacement. So if we divide this ds by dt, the incremental time change, we will be getting velocity, right? So, but obviously that will be the magnitude of velocity. Velocity will have a certain direction also. So if I divide ds by dt, I will be getting the magnitude of velocity, right? So v will not be vector. If I simply carry out this division, the arc length divided by dt, the time in which that change in position occurred, right? This will actually give me rho times d beta divided by dt, right? And this thing I can denote it with a different symbol. I can call it as rho times beta dot, right? Where dot actually means the first derivative of that quantity with respect to time, right? So the magnitude of velocity is rho times beta dot, right? What about the direction of velocity? By looking at this figure on the right side, can you see what will be the t component of velocity and what will be the n component of velocity? Velocity will always be having t component, it won't be having any n component, because we have seen already that velocity is tangent to the path, right? And it is the same direction in which our t axis is, right? So velocity won't have any component in n direction, it will all be in the t direction. But acceleration is neither tangent to path and nor normal to path. We have seen that in the introduction to plane curvilinear motion, that acceleration's direction depends on the change in velocity, and that change in velocity is neither tangent to path nor normal to path, which means that at any time instant acceleration vector will have both components, or it can have both components, right, along t and along n. But velocity will always be in along t direction, it won't have any n direction component, it will not have any component along n axis, right, because it is always tangent to path. At any time instant the direction of velocity is tangent to path, which means it will have only one direction all the time, and that direction will be the t direction, right? So while I can say that the magnitude of velocity is rho times beta dot, the direction of velocity is always towards this unit vector E sub t, right? So the direction of this is magnitude of v, this is magnitude of v vector, but what about direction of v vector? Direction of v vector, right, will be given by this vector E sub t, right, this unit vector E sub t, right. So we can write velocity in the vector form as v vector is equal to this magnitude rho times beta dot, and the direction will be multiplied and it will be E sub t unit vector, right. So this will actually be the complete description of velocity in n-t coordinate system, right. It doesn't have a second component which is in the direction of E sub n, right. It only have one term and that term is in the direction of tangent, right. So that's how in this equation at the bottom we describe velocity vector in terms of n-t coordinates, right. Now the whole idea is that this E sub t is not a constant vector, it is changing its direction all the time, right, and therefore velocity is also changing its direction all the time. E sub t will have a magnitude equal to 1, right. Now let's move forward and see how we can write acceleration in terms of n and t coordinates. And as I said earlier, now you will see that acceleration will have two components. One will be along t axis, one will be along n axis. So let's start how we can write acceleration in this coordinate system. Acceleration vector is actually the first derivative of velocity vector with respect to time, right. So we have already seen what is v vector, it is this quantity. So let's take its first derivative with respect to time. This will become d by dt of rho times beta dot times E sub t unit vector, right. So it is a product of a scalar quantity rho times beta dot times the vector quantity, right. So E sub t is a vector, rho beta dot is a scalar quantity, right. We can evaluate this differentiation now. If I just call this as small v without a cap on it, it becomes the magnitude of velocity. So it becomes d by dt of v times E sub t, right, this thing where v is the magnitude of velocity. This will become dv by dt times E sub t plus d of E sub t by dt times the v, right. And in other words it will become, for example, I can write that term first. So it will become v E sub t, the first derivative of E sub t. So I am putting a dot on E sub t, right. So this is actually the first derivative of E sub t with respect to time plus this term. So this will become v dot, right. So v dot times E sub t, right. So this is my A vector now, right. I can write it clearly. A vector is v times E sub t cap and then dot plus v dot times E sub t, right. So this is my acceleration vector, right, in n-t coordinate system. It has two terms now, but the direction of both terms is not clear. For one term it is clear. Now we know that this term have a direction of tangent t axis because it is being multiplied by the E sub t. But here we are having first derivative of E sub t with respect to time. So this E sub t, first derivative of that quantity is actually d by dt of E sub t, right. Now unlike the xy coordinate system where the first derivative of I and j were 0 with respect to time, so you remember that we saw that di over dt is equal to 0, and similarly dj over dt was also 0, right? Because I and j were having a constant magnitude and a constant direction. So their time rate of change should be 0, but not in this case, right? Not in this case, because E sub t is changing its direction, although its magnitude is still constant 1, but it is changing its direction. So we cannot simply put this quantity as 0 in acceleration term, right? So if you look at the second part, you have the v dot, which is the time rate of change of speed, right? But the first part contains the first derivative of E sub t with respect to time. So it means that in order to describe acceleration as a sum of some t direction component and n direction component, we need to evaluate the value of this quantity and then put it back here, because we already have its t direction component but no n direction component, right? So we need to now calculate or evaluate this differentiation, or what will be the first derivative of E sub t with respect to time. And then we can come back to this equation, put it here, and then that will be the complete description of acceleration vector in nt coordinates, right? So the main point is that this derivative is not 0, it need to be determined. So in order to determine this derivative, time derivative of E sub t or d by dt of E sub t cap, what I did here is that I simply took this E sub t vector from this figure, and obviously there will be some new E sub t here. Let's call it E sub t prime vector, right? So the unit vector in the direction tangent direction when particle was at point A is denoted by E sub t, but the unit vector in the tangent direction when particle was at A prime was E sub t prime, right? So what I did, that I started this E sub t and E sub t prime from the same origin or same starting point, right? And this give me this triangle actually, that from the same point I start E sub t, and from the same point I start E sub t prime, right? So again I can write it here that E sub t is the unit vector in t direction when particle was at A, right? When particle was at A, and E sub t prime is the same unit vector in t direction when particle was at A prime, right? So particle at A prime, and I simply draw it such that they both start from the same point, right? Now we know that the angle which the normal component or normal direction n direction is making at the center of curvature, this angle is d beta, right, between A and A prime. And since the tangent is always perpendicular to that normal, so the angle which the ET and ET prime is making with each other should also be d beta, right? So if the normal components at both locations are making an angle d beta with each other, their perpendicular directions will also be making the same angle d beta, right, between each other. So the angle between ET and ET prime will also be d beta, right? This configuration or this geometry will give us actually the change in the E sub t between time t and t plus dt or during the time dt, right? That change in the unit vector from A to A prime will be represented by this vector det, right? So det is the change in the unit vector. Obviously the change is only in the direction, the change is not in the magnitude. So magnitude of this Et is 1, so I can write that E sub t, magnitude of that, or E prime sub t, both magnitudes are equal to 1 actually, right? And det, right, is actually the change in change in E sub t, right, during dt, right. With this representation now, I can determine the direction and magnitude of this change in Et and determine the first derivative or rate of change of that quantity with respect to time. So for example, I can say that here the magnitude of this change det, right, is simply equal to the length of the arc which this E sub t vector is making in rotating an angle of d beta, right. So it is length of the arc which E sub t vector is making while having an angle of or rotating with an angle of, right, with d beta angle, right, rotating with angle d beta, right, and that simply should be equal to length of the E sub t multiplied by the angle, right, L is equal to r theta. So we can determine the length of this vector denoted as the magnitude of this vector here as the magnitude of this vector, which is the radius here, E sub t, times the angle which is d beta, right, d beta. So first thing I can determine is the length of this quantity, and then I can simply divide it with dt to calculate the first derivative of this vector with respect to time. So the length is simply 1 times d beta, because the magnitude of the unit vector is 1, so it is simply d beta, right, d beta. So the length of this vector, this distance for example if I write, that is d beta, right. The second thing is the direction of this det. If you look closely, you will find that the direction of det will be the direction of normal component or n-axis. If I go back here, so see, if I start both Et and Et prime from this point and then draw their difference, right, det, and that det will actually point towards center of curvature, which means the direction of this vector det will be the n-axis or n direction, right. So I again go back to the figure and you can see that what I did, I start the E sub t vector from a point, I start the E prime sub t vector from the same a point and then draw the difference. The difference is pointing towards center of curvature or towards n axis, right. So here this is E sub n, the n direction, the unit vector in n direction, and exactly the same direction you can see here is the direction of dE sub t, right. So this direction actually is the n direction, right, and the n direction is denoted by a unit vector in n direction, and that is E sub n, right. So in short, the direction of this det vector is the n direction or in the direction of unit vector E sub n. So finally, if I write this det vector as a product of its magnitude and its direction, it would be simply det magnitude times its direction, and that direction is in the n direction or n axis. So E sub n is describing the direction of this det. Now magnitude is simply d beta, and we have E sub n here, right. This will give me dE sub t, right. So now I describe this whole vector det as its magnitude times its direction. Now I am ready to divide it with dt to calculate its derivative with respect to time, right. So what I am doing now is I am taking this equation down here, maybe at this location, and simply dividing it with dt. So dE sub t divided by dt it should give me d beta by dt times e sub n, right? So this will be the first derivative of unit vector et. Now I can put it back in my acceleration equation to complete the description of acceleration in n-t coordinates, right? So in the symbols which I was using earlier, this equation will finally become e sub t dot, the first derivative of unit vector with respect to time, is equal to beta dot, first derivative of beta with respect to time, times e sub n unit vector, right? So this bottom equation which I am highlighting now is my final takeaway from that whole exercise, that I can now describe the first derivative of the e sub t or unit vector in t direction in terms of e sub n direction, and now I can put it in my acceleration equation, which was this equation at the bottom, right? This equation at the bottom. So we have determined this quantity now, right? We can put this quantity and our acceleration equation will now become, for example, I can now put this quantity in acceleration and it will become a vector is equal to, actually it was e sub t dot plus v dot e sub t. I can put this quantity as, if I go back, it is beta dot times e sub n, so it is beta dot times e sub n, right? So the final equation will become v beta dot times e sub n plus v dot e sub t, right? Now this form of acceleration is telling us that we have described acceleration as a sum of two components. One component is along t and one is along n. So now this is my final acceleration equation. Now it is in the form of something times e sub n plus something times e sub t, right? So I can call this quantity as the t component, the magnitude of the t component of acceleration, and this quantity as the magnitude of the n component of acceleration. Is similar to what I write, for example, x dot dot times I plus y dot dot times j, right? So I have written acceleration as a sum of two components, one along one of the axis, one along the other axis, right? So this v dot is the magnitude of the t component of acceleration, right? T component of acceleration. In scalar terms, I can call it like a sub t, right? The t component of acceleration. Similarly, this quantity I can call it as a sub n, the n component, the magnitude of n component of acceleration vector, right? So some of the other scalar equations which you will be using in this topic, it will become actually, for example, in the velocity case, if you remember, we wrote v here as in the last slide. So you remember that v is equal to rho beta dot, this term. The magnitude of velocity will be rho times beta dot. So let's use that equation here to come up with more variations of the same equation. So v is beta dot, let me just confirm it, v was equal to rho times beta dot, right? So v is rho times beta dot, right? So beta dot can be written as v over rho here, right? So when I introduce this beta dot in the acceleration equation, it will become, acceleration will become v square over rho times e sub n plus v dot e sub t, right? So this v square over rho can also be, it is same as a sub n, right? So a sub n is equal to v beta dot or v square over rho, same thing, right? Similarly, there is another variation. We know that a sub n is v square over rho, right? We can put this v is equal to rho beta here, so it become rho beta square whole thing divided by rho. This will become rho times, sorry, it is beta dot, rho times beta dot square, right? So a sub n can be written in 3 or 4 forms. It can be written as v times beta dot, it can be written as v square over rho, or it can also be written as rho times beta dot square, right? But v dot, which is simply a sub t, is simply first derivative of magnitude of velocity with respect to time, or it is the rate of change of speed, right? It can also be represented by s double dot, right, where s is the speed, right? Finally, if we have written acceleration as a sum of two vectors, one along t, one along n, we can also write that the magnitude of acceleration vector will be simply, the magnitude of a vector will be simply a, and that will be a sub n square plus a sub t square, right? So I can determine the n and t components of acceleration at any given time using any of these expressions, and then put them in that equation to determine acceleration amplitude or magnitude, right? One last thing in this acceleration representation is that this a sub t, which is actually equal to v dot, this thing, can also be written in another form. So let me just write it, maybe separate it here and write it here. So a sub t can also be written as the first derivative of velocity, and if we simply put beta into rho dot, beta dot into rho here, right? So beta dot into rho, and we can take the derivative of this product to get a new equation, and that will be rho times beta double dot plus rho dot beta dot. That is a relatively complex representation of the a sub t, or the tangential component of the acceleration vector, right? But we don't use it. Most commonly are using actually a sub t is equal to the time rate of change of speed, right? So v dot. So all clear that we have described our acceleration vector in terms of its sum of its t component and n component, right? Both of these quantities a sub n and a sub t will be having acceleration units, because they are the magnitudes of the two acceleration components, right? So this quantity should have an acceleration units, right? This is a sub t, so acceleration unit, and this whole quantity v times beta dot should have an acceleration unit. What will be the units of b dot? Rate of change of angle with respect to time. Radians per second or degrees per second, right? And what is v? Meter per second. So it becomes meter per second square. Radian is actually the number. It is not something which will modify your unit system, right? Now you will be facing problems in which the situation will tell you that you should describe this curvilinear motion using nt coordinates, right? The geometry of that motion will tell you straight away that it is a case of using nt coordinates, and you will be calculating the n component of acceleration separately, t component of acceleration separately at some given time, and then combine them using this equation, right? So this equation can be also written as like a sub n times en plus a sub t times et, right? So you are simply combining both components to get the a vector, right? For velocity, it's a simple case. Velocity only have one component, so v vector will be simply rho times beta dot times e sub t unit vector, right? It won't have a term involving e sub n, but acceleration have both terms, right? So now let's quickly summarize what we have discussed up till now. A sub n is the n component of A. It is always directed towards the center of curvature, right? A sub t is the t component of A, and it will be having the direction of positive t when the speed is increasing, and it will be having a negative t direction if the speed is decreasing, right? So at any time instant, if for example this is the motion, you can have some a vector and then you have a t component and some normal component. Normal component will be facing towards the center of curvature. When the curvature change, the direction of a vector also change, such that now the positive normal is towards the new center of curvature, right? At the point of inflection, the normal component will become 0, because you can see from this equation, this is your a sub n, which can also be written as v square over rho, right? So when you are exactly at the point of inflection, then what happens? Actually rho will become infinity. So if for example you are having a motion like this, and exactly at this point you have the point of inflection, right? So you will see that there is no curvature here, right? So theoretically rho becomes infinity at this point. The radius of curvature will become infinity, right? So when you will put it here, obviously you will get a sub n, which will be approaching 0. So at point of inflection, a sub n actually approach 0, and you will only having the acceleration in the tangential direction only, right? So you will only be having a sub t. One more description of both components in a slightly different form to clear concepts. A sub n represents the component of acceleration responsible for changing the direction of velocity vector as the particle moves along the path. So since a sub n is in the e sub n direction, right? So and a sub t is in the e sub t direction, velocity is actually only in the t direction. So a sub t represents the component of acceleration which is responsible for changing the speed of particle. So a sub t is related to speed of particle, right? If it is increasing, it is in the positive t. If it is decreasing, it is in negative t, right? And therefore it is actually a sub t, you see that it is equal to v dot, right? So the effect of change in speed of particle is captured by a sub t, right? But the effect of change in direction of velocity is captured by a sub n. So you can also describe both components in these terms also, that when the particle is moving from a to a prime, velocity is changing from v to v prime, right? But velocity can change in two ways. Its magnitude can change and its direction can change. So the change in magnitude of that velocity is taken care by this component of acceleration a sub t, and the change in the direction of velocity is taken care by this a sub n, right? So this is another kind of representation or concept associated with a sub n and a sub t, right? We discussed that the n component of acceleration will always be towards the center of curvature, right? So if I write n towards the center of curvature, and t component, right? The t component or a sub t will be positive, right? Or it will be towards positive t direction when velocity increasing, right? So when v is increasing, speed is increasing, actually the magnitude of velocity is increasing, right? Increasing. And the a sub t will be in negative t direction when v is decreasing, right? Decreasing. So let's quickly see in different cases how the acceleration vector will orient in both cases. So what I did is that in this figure, one particle is moving from this point to this point, then this point, and all along this path, right? and this black arrow shows the acceleration vector at all these points, right? So at this point the black arrow is in this direction. I can write it as a sum of its t component and n component, right? So this will be its t component, this will be its n component, right? So n component, as we have seen, it is in the direction of center of curvature because it is concave upward, this curve, right? But t component is in the positive t direction, right? Positive t direction. So therefore this acceleration is representing a motion which is having an increasing speed, right? Similarly, the particle moves to the next point, and again I can take a tangent to the path and normal to the path and can write this acceleration vector as a sum of these two vectors, one along t, one along n, right? N is again towards the center of curvature, but t is also again positive, right? And here this is the point of inflection. It only have one component, which is the t component, right? And that is the only component, there is no n component. Here at this point again I can take a tangent, so this will be t, this will be n. N is now directing towards center of curvature, which shift to somewhere here, right? Previously it was somewhere here. So now the center of curvature change, n component also change. T is still in positive direction, t component is still in positive t direction, which means this is the case of increasing acceleration, increasing velocity, increasing speed. Similarly at this point I can have a tangent and a normal. Tangent component will be like this, normal will be like this. So which means that this whole motion all along this whole path, it is a case of increasing speed, right? And the right hand side, if you look, again the black arrows are showing the acceleration vector at different points. Let's now write the n and t components, the directions of n and t components of that acceleration. So at this point I can take a tangent, this will be my t component of acceleration and this will be my n component of acceleration. Now n is again towards the center of curvature, but t is now in the negative t direction. So now a sub t is in minus t direction in this case. Similarly here also t component will be this, n will be this, right? This is the point of inflection. This is again t component will be like this, n component will be like this. So t is again negative t direction, t component. Similarly this will be my t component in this case and that will be my n component. So n is always facing towards center of curvature, but in this whole motion, right side of this figure, this whole motion, the t component of acceleration is in the negative t direction. So which means this is a case of decreasing speed, right? So this is whole motion which is decreasing its speed with time, right? So by looking at the direction of the components of acceleration, you can tell whether the motion is having an increasing speed or decreasing speed.